See, we are going to start with this lesson since it's a very short class, so we'll be having the introduction only of this lesson. That is your chapter number 3 of current electricity. So a very short class, we have duration is very short, so we'll be just starting with the introduction portion. After the class, once this class gets over, we'll be completing this lesson in your regular batches. In whichever batch you place, we'll continue from here. And the backup will be provided to you for the first and second lesson, because obviously with the first lesson we cannot start it now, as you also know.
Right.
Aymaan, just tell me one thing. What's currently going in your physics in your school? It must be vacation, no, right now?
Yes, I'm in summer vacation, and the last thing we did was start chapter 4.
You had completed chapter 4, magnetic.
No, we started it.
You started it. Okay, so it means chapter 3 has been completed. Fine.
Yes.
So it's okay if we start with chapter 3, that will be fine. All right. So now see, the first topic in electrostatics when we study means charges when they are at rest. That is electric charge, which is the basic or intrinsic property of matter, and that gives rise to different or various phenomena. Now what will happen in case of current electricity? Current electricity has the basic unit as the electric current. The way electric charge becomes the basic unit for electrostatics. When we come into chapter number 3, that is your current electricity, here you can use the terms like velocity, acceleration for the charges, which were prohibited in case of electrostatics. Rufia, your class is half an hour later, no? Or you just come for the backup? Rufia, Sayyida Rufi.
Yes, ma'am. Okay, I'll come later.
Okay, because it's just an introductory class going on. So you can join in later, 20 minutes later, half an hour later, you can join. Fine, and you're at your usual timings. All right.
Okay.
Now, see, electric current is basically what? If I start with this term electric current. So electric current basically means the flow of charges and rate of flow of charges, to be precise. Now, why are we using the term rate? Anything or any quantity that gets divided by time, we call it as rate. You might have done this in your 11th standard when you were studying velocity. You had studied that velocity is rate of change of displacement. It means displacement divided by time was velocity, or acceleration is rate of change of velocity. That means velocity divided by time is acceleration. Similarly, electric current is also rate of flow of charges. That is charges divided by the time. So electric current's basic definition becomes rate of flow of charges. This is the basic definition of it. Now, rate of flow of charges in reality means what? Like if I take a conducting wire I have taken. So I have drawn it thicker. This is just a simple wire like this. A thin wire like this, which we use in our circuits, a wire like this. If we take this wire and at t is equal to 0, I have started the timer. And exactly at t is equal to 1 second, I have stopped the timer. Some amount of charges have flown through it. I have noticed this. Some amount of charges have flown through it in 1 second. Now, according to this definition, the formula of current becomes charge divided by time. Whatever is the flow of charges, that divided by time. Now, if I put t is equal to 1 second, can you tell me what will be the relation left in this formula if I put t as 1?
I is equal to Q.
I is equal to Q. Perfect. I will be equal to Q. It means you can define electric current like this also, that electric current is the total charge that flows through a conductor within duration of 1 second. So these are the basic two definitions of electric current. Now, electric current's SI unit is also important to know. SI unit is ampere. By the name of the scientist, ampere is used. And this is denoted through capital U. Current symbol is I. We'll be using this term symbol I. But the SI unit means 1 coulomb divided by 1 second. This term. This is known as 1 ampere. Also, second important thing in this is the quantity, type of quantity that it belongs. See, physical quantities are basically categorized as vector quantities and scalar quantities. Vector quantities are those quantities that have the magnitude as well as a specified direction associated with them. Regarding scalar quantities are those quantities that just have the magnitude with them. But remember, there is only and only one exception to this scalar quantities case, and that is the case of this electric current. It means electric current is a scalar quantity, but it has a direction. So scalar quantities do not have direction, but electric current is the only quantity that has direction, but we call it as a scalar. But so now what's the reason for calling it as a scalar quantity? If it has a direction, magnitude could be calculated using this formula, then why do we not put it under the category of scalar quantities? The reason behind this is that though it has a direction, but it does not obey the vector laws. Vector laws, you must have done it in your 11th standard: parallelogram law, triangle law, polygon law, all those vector laws of addition. Current follows algebraic addition, algebraic subtraction. That's why we do not put it under vector quantities despite current having its direction. Now, what is the, don't write anything right now. I'll give you sufficient time to note down these things.
Okay.
Regarding the direction of current is very easy to remember because it's, as I've told you, this is not a vector quantity, means it doesn't obey the vector laws. So you need not worry about the angle that it is making between two currents and everything. If it is a positive charge, for positive charges, let's say this is the motion of charge is moving, let's say, towards the right hand side. In this direction the charge is moving. For positive charges, the direction of current is same as that of charge. It means current will also move towards the right hand side. For positive charges, current has same direction. This is the first point. Now regarding negative charge is all those negative entities like electrons. Especially this is valid for electrons, because in current electricity throughout we'll be focusing majorly on electron. So negative charges like electron, if they are supposedly moving towards the right hand side with some velocity v, direction of current becomes opposite. Direction of current goes in this way, means it will be opposite to that of motion. If the charge is moving up, the negative charge is moving upwards, the direction of current becomes downwards. It becomes exactly opposite. So for negative charges, current has opposite direction. Clear till here?
Yes, ma'am.
All right, do one thing, note these points first, and we'll see further how to use this formula. There are slight variations in this formula as well, but just don't note down this first.
Done till here. Yes, I'm done.
All right. So these are the basic points. Now, just focusing on the formula portion. That's what we'll do, and I'll then stop. The formula portion basically, see, I is equal to Q by T, you are aware of. There are two things in which way this formula is used, because I is equal to Q by T is very basic. In your board exams for class 12th, or even in the exams that you appear after class 12th, be it NEET, JEE, or any other university exam, or even in your class 12 simple exam, you can get time in two ways. Either it can be a time interval. Time interval means from beginning from one time to ending at another time. Like I will say zero, calculate the current at 0 to 2 seconds, or calculate the current in between 5 to 8 seconds. Like this, a duration is there, a time interval. We call this as an interval, where there's a beginning of the time and the termination time. So this we call as the time interval. Let's say example 0 to 2 seconds. This is an example. So here we take the difference of the final charge minus initial charge, means difference of the charges, that is Q final minus Q initial. Q final means charge at 2 seconds minus charge at 0 seconds divided by the time interval. So in this case, it will become 2 minus 0, that is 2 seconds, like this. And the current that we get, no, this current that we get on calculation of time interval, we call this as an average current. So in your questions, if you are asked to calculate average current, or if it is mentioned the time as a time interval, then you will be using delta Q divided by delta T. It means change in the charge divided by the change in the time interval. Second thing to this is the time instant. Not considering 0 to 2 seconds like this. If I say, tell me what is the current exactly at T is equal to 4.01 seconds, like this. So that's not a time interval. At a specific time, be it T is equal to 3 seconds, or be it a very small number like T is equal to 0.00001 seconds, like this, infinitesimally small number. So if supposedly time instant is mentioned to you, then you cannot use I is equal to Q by T. Neither you can use I is equal to Q by T, nor you can use delta Q by delta T. Time instant means at a specific time. It can be huge, like T is equal to 1000 seconds, T is equal to 5000 seconds, but exactly at a time instant. Or it can be a very less quantity, which is infinitesimally small. Infinitesimally small, whenever we use this term in physics or in mathematics, that means quantity which, if you put around 20 to 30 zeros, no, in between point, decimal point, and that single digit number, then also we'll consider it as a number. I think in class 11th in your chemistry as well as in physics also, we had this topic significant figures. From there you can relate it to it. So time instant means at a very, very specific time. Like example, T at 2 seconds, time is equal to 2 seconds. So that becomes the time instant. So this is the difference between time interval and time instant. Now in case of time instant, we differentiate it, dq over dt. We differentiate charge with respect to time. And the kind of current that we obtain, this is known as instantaneous. Are we clear till here?
Yes. Can you give me an example of calculating?
I'll just, yes. I have the example with me. I have this example. See, this is a question given to you. Q is 3t square plus 2t plus 1. Current, you have to, in the first part, find out current between 0 to 2 seconds and current at t is equal to 2 seconds. So now you tell me, in the first part, is it time interval mentioned or time instant mentioned?
Time interval.
Interval is mentioned. It means we have to find out the current. So charge for the first part at between these two, let's calculate the current first at t is equal to 2 seconds. It means we have to put 2 everywhere in this equation. This is the final charge that we are calculating because this is the final time. So instead of t, put 2 everywhere. That becomes 2 square plus, instead of again t, we'll put 2 multiplied by 2 plus 1. This gives us what? This is 4 into 3, 12. 12 plus 4 becomes 16 plus 1, 17 coulombs. Now, this was the final time. Now, initial time was 0 seconds. So, Q initial becomes what? Instead of T, we'll be putting 0 everywhere. So, here this becomes 0, this becomes 0, 0. We only have 1. Now, see what your current will be. This is delta Q divided by delta T. Remember, we agreed with the fact that if time interval is there, we have to calculate the average current. So, this is the average current that we are calculating. How do we calculate the change? Final minus initial divided by the time interval, time final minus time initial. That becomes 17 minus 1 divided by 2 minus 0. That is 16 divided by 2, which is 8 amperes. First element. Is this part clear?
Yes, ma'am.
All right. Now, second part says exactly at t is equal to 2 seconds. So, this is the time instant. So, our equation is what? For the second part, equation is given as 3t square plus 2t plus 1. How are you with the differentiation and the integration with the calculus question? Is it clear to you?
Yes,
Or
it's
you're
clear.
still?
No, it's clear to me.
All right, all right. So if we differentiate this equation, dq over dt, so can you tell me what will be the differentiation of this portion?
3 2t
3
2
2t t, exactly. Plus, and this
2
2, and this will be
0.
0. Perfect. Your differentiation is perfect. So this becomes 60 plus 2. This is the equation of current. Now you have to put in the value for at t is equal to 2 seconds. Your current will be 6 into 2 plus 2. That gives what? 14 amperes. Fine. Did you understand the difference?
Yes, I did, ma'am.
All right. So just note down these portions as well. This example as well as these lines. And wherever you are having difficulties, ask me freely.
Okay. Yes, I'm done now.
All right, fine. Then you can leave it for today. So we'll meet